Morning, guys. So I just wanted to review with you some of the main concepts that we learned in our energy section. For starters, we define energy. Things that have energy have the ability to do work. Now, one key note for energy here is energy is actually a scalar. In comparison to all the vectors that we've been learning, displacement, velocity, acceleration, forces, impulse, all those being vectors, scalars here, remember, they only have magnitude, meaning they only have a size, meaning there's no component work, there's no breaking up of vectors. In that sense here, it should be much easier. However, this energy can come to us in many different forms. We started looking at kinetic energy a little bit in the momentum section. We did potential energy in this chapter with roller coaster problems. We'll see that in this review here. But basically, it's just a number. Usually we treat that number here as positive. Positive and negative for energy actually means something a little bit different. We'll see that in the first question here. We're also going to be really technical in the way we define work. Work is going to be defined, one formula here is force times distance. So basically, if I apply a force and I use it to drag an object, depending on how far I drag that, I multiply those two, F times D together, and that is actually referred to as work. Sometimes you'll be given more information to actually calculate as a change in energy. So both of these formulas here work to calculate work. But basically, it just depends on the exact problem itself. So let's just start off with an example of this F dot D sort of formulation. Let's do a elevator style question. For an elevator style problem here, let's imagine I'm standing at the bottom inside an elevator. This elevator here is going to be pulled upwards by some tension. I'm going to ask you to calculate that in a second. Let's say we are a 55 kilogram object. Although the elevator around me is much heavier, I basically accelerate with the elevator. As the elevator goes upwards, I'm going to get pushed up along with it. Let's say after you press the button in the elevator here, the acceleration rate at this point here happens to be 2 meters per second squared. After every second, you speed up by 2 meters per second. And let's say to reach my floor, we end up accelerating for a total distance of 10 meters. I want to know in this question here, see if you can find the work done by gravity. Right? Gravity is always a force that's constantly trying to pull you towards the center of the earth. Done by gravity. What's the work done by tension? So the string that's actually pulling this cable that's actually lugging this elevator upwards. And what's the net work? So if those two works compete against each other, overall, how long has your task taken? Part B here, I'm going to ask you to calculate for me calculate the overall power. Remember, power by definition, power was you're trying to accomplish a task of work. You're trying to drag you up these 10 meters here, but divided by how long it takes you to do it. Do that division there and you found power. And let's say this elevator here, let's say as I'm paying my electricity bill, I sort of know what energy rating this elevator should be going up at. If the power input was 500 watts, I want you to determine the efficiency. Remember, we live in the real world, so basically nothing is perfectly efficient. So you may be delivering 500. This W here actually stands for watt. That is the unit for power. And that watt there actually implies a joule every second. So technically this elevator is rated every second. It's supposed to be delivering 500 joules. Depending on what you calculate in B, you might actually find how much was actually delivered is actually less than that. To find efficiency, we're going to use this eta symbol. And basically it's a ratio. You can be sort of energy in divided by, energy out divided by energy in. In this case here, because we have it framed in power, let's figure out how much power output did I get versus the input of 500 that I actually put in. I'd encourage you to pause the video and try it out for yourself. And then when you come back, you can check your work here. For starters here, we need to find the work done by gravity. So because I'm given distances here, I'm sort of thinking, oh, I want to do work as F dot D, right? As opposed to work as change in energy. We'll do that more for roller coaster style problems. I'm going to start off with a free body diagram. I am a 55 kilogram object. There's gravity that's acting on me. Fg is equal to mg. So 55 times 9.8. This gives me here 55 times 9.8 is 539. gravity is constantly pulling you downwards at 539. Remember, in our dynamics chapter, we don't need to worry about positive negatives because my free body diagram actually indicates to me the direction for me. The other force that's being applied on me is a tension force. Tension is pulling upwards. There is no formula for tension. However, because I sort of know the answer, I know that between the tug of war, it is just tension fighting against Fg. Because I know my acceleration ends up upwards, that actually hints to me that the tension is actually larger. Because later on they will be asking for the net force anyways. Let's just calculate the numerical value for net force. Newton's second law, F net is equal to ma. For my mass of 55 kilograms, yes, the elevator would also have mass as well, but me that's accelerating along with the elevator, 55 times 2 is equal to 110. I need to have an overall wind, an unbalanced force of 110 going in the upward direction. Remember, net force by itself is just a magnitude. It's just the overall unbalanced force. This time, my net force is tug of war between tension and gravity. And because I know gravity already, gravity here actually has to be 539. I can actually find then, therefore tension needs to be not just a 539. It needs to counteract gravity. At that point here, it would just cancel out gravity. But it needs to give me a net win of 110. And therefore, 539 plus 110, I found that the size of the tension force has to be 649 newtons. All right? So just a little bit of dynamics work here to actually get to that those forces there. When we use this formula here, F dot D, it has to be just the parallel part. So if I had forces that were pulling horizontally, those won't count. This time here, I'm pulling upwards, I accelerate upwards, so that counts. The gravity here, as the elevator slides upwards here, gravity is constantly also parallel to it, so all of this one here counts. There's no component work that's needed. So let's try it out here. What's the work done by my cable itself? Well, it's the tension, it's the force along the string here, multiplied by the distance. In this case here, I actually do know the distance here is 10 meters, so I could just multiply that there. So the tension in the cable here is 649. It needed to be bigger than gravity and also give you that net force to accelerate. I do that for 10 meters here. 649 times 10 gives you 6490. That's the total amount of energy, the work that I applied to actually lift you up. The work done by gravity is going against me, Fg times distance here. I'm going to put a negative there because this one here is actually going against me, negative 539. It sort of acts like a friction force. That's going to remove 5390 joules worth of energy. Wait, I thought we said energy has to be a scalar. I thought it has to be positive. Remember, energy, positive, negative means something different. Whenever energy is positive, this one here just means energy input, right? I'm actually rolling the cable so that I actually put in 6,400, but because I'm fighting against gravity, gravity then removes 5390. This is energy lost to the surroundings. We're always fighting this losing battle here. And therefore, to calculate the net work, you can do it one of two ways. To calculate the net work here, you can just do net force times the distance. We already knew that the net force had to have a magnitude of 110. You can say 110 being supplied at 10. This is going to be 1,100. Or what you're going to find here is because these were scalars, if you did the subtraction 6490 minus 5390, that would equally well give you the total amount of tasks that you accomplished was 1100. I actually put in 6400, but I actually needed to fight against gravity. So remember, when you use this formula here, it's only the parallel force that counts. Alright, so now that's part A. For part B of the problem here, I need to actually take this work here overall, so the net amount of tasks that I accomplished was the 1100. I need to just calculate how long did this take. So a little bit of kinematic work for us here. I imagine that this elevator here started from rest. It has an acceleration rate of 2. Let's see if we can find, if I want to travel 10, v naught t plus 1/2 at squared. If I need to travel up by 10, my initial speed, I'm going to assume that we started from rest, so 0 times time is just going to kill that term off. This has to equal to 1/2. My acceleration rate here is 2, because my elevator is actually going upwards at 2. Times it by t squared here. 10 times 2 divided by 2 doesn't do anything. Essentially, the t is going to be the root of 10, and therefore the time is actually 3.2 seconds. So as this cable here constantly accelerates the elevator upwards, it's going to take 3.2 seconds for you to travel this 10 meter worth of distance. So for part B, you're going to then find how much power output did this elevator actually give you, work divided by time. I ended up getting only 1100 joules of useful work. It took 3.2 seconds to do that. 1100 divided by this time here, this gives me roughly 348 watts. For every second I was able to deliver 300, so about 3 seconds of time I deliver a little over 1100. Now my elevator again had a power rating. There was a true ideal, the electricity that I was putting in. For efficiency, we do how much power output did I get versus how much did I put in. I just calculated the true amount that I got lifting the elevator was 348. I actually put in a power rating here of 500 watts. It was supposed to deliver electricity 500 joules for every second. Notably, I've actually lost some. This ends up as a decimal, so I'm going to multiply by 100 to get a percent. 348, give or take a little bit of rounding, I'm getting roughly about 69.5, so 70%. Right, and that is my efficiency. I actually lose a little bit of the energy, maybe due to sound, maybe due to heat, maybe due to light. The total energy has to be conserved, but not all useful for actually dealing with my system. Right, so that was some nice practice here using the formula. Work is equal to force times distance. As we switch over to take a look at potential energy concepts, let's do a roller coaster style question. So for a roller coaster here, let's just do this by example. We start off on a roller coaster. Let's say the first hill, I don't know how tall this is, but I know that the roller coaster, we just get dragged to the top of the hill. So this one here currently is at rest. I'm told later on, my roller coaster actually is a 500 kilogram object, and it's actually zipping by. This second hill that it zips by here is 30 meters, and the velocity that I'm going at is 20 meters per second. Right? So that's the information given. Again, I'm going to give you A, B at this question here. Part A, calculate the total energy at the beginning. Right? What amount of energy did I have to start off with? Okay. Part B, I want you to calculate for me, find the height of the initial hill. Right, so find the h that I've listed for you there. And part C, I want you to find or determine the max speed. And intuitively you'd say, well, the roller coaster would sort of speed up on the way down. Our maximum speed here should be when we're actually on the bottom here. Just to throw in a quick bone as you do this here, usually we deal with energy is conserved, so E in equals E out. In this case here, let's say during this first part of the motion here, let's say there's actually energy lost due to friction or due to sound as people are screaming on the roller coaster here. Let's say we end up losing about 10,000 joules. And just for simplicity, although that technically would apply to the entire motion, let's just say it was applied during this part of the motion so that we can do the problem. So again, I encourage you to just try it out for yourself, pause the video, and then let's try it. Usually I would start off with where I know more information. I know a lot of information at the second hill. At the second hill, we are some distance off the ground. So if I wanted to calculate here for part A, the E total is actually split between, because I'm 30 meters off the ground, I have some potential energy, and I also have some kinetic energy. For potential energy, we have the formula, potential energy is mgh. For kinetic energy, we already saw last chapter, is half mv squared. So because I know a lot about this part here, let's just calculate it. If I'm a mass of 500, I'm going to assume the acceleration is 9.8. I'm on the Earth's surface. I'm 30 meters from the ground. How much is stored up in my potential energy account? In my other account here, I have 500. The velocity here is going to be times 20 squared. I'm going to just calculate these values here separately so you know how much is in each of the accounts. First account here was 147,000. The other account, 0.5 times 500 times 20 squared. This gives me another 100,000. So remember, we had this sort of bank account analogy here. I have these two bank accounts. I have 147,000 in one account, 100,000 in the other account. In total, my bank account, I have $247,000, or joules in this case here. That is the total amount of energy that we have at this point here. That's part A, right? And we'll actually slightly different for part A. In part A here, it's the beginning. We would have said E in is equal to E out. So I want you to do this here. just thinking about this formulation here, work is supposed to be a change in energy. Change in energy should be E final minus E initial. I'm just going to bring the E initial over to the left side. So E initial plus work is equal to E final. Very similar to our impulse formulation here. Essentially, the E in is supposed to equal to EF. The only thing that can change it is if you do some non-conservative work. A non-conservative work in this case here is like air resistance. Because I've actually lost a little bit of the energy due to air resistance, due to people screaming on the roller coaster here, I actually removed some of the work. But were it not for that, these E in should equal E out. They give this formula a fancy name here. They call this one here the work energy theorem. But basically, it's just a slight manipulation of the work formula that we already had. So if at this point here on the second hill I have 247,000 and I lost 10,000 going down, I can figure it out here. Actually, for part A, part A would actually have the 247,000. So actually, my total energy, this is at the beginning. I already calculated. I still had 247,000 on the second hill, but I want to gain back that 10,000 I had lost, and that should give me here 257,000 joules. Right? So that's how you deal with if I have a non-conservative work like air resistance. So at the beginning, before I lost energy, I had 257,000. Because at the beginning I'm also at rest, I've transferred all the money in my kinetic account all to potential. So at the top of the hill, we have the entire energy amount actually as mgh like that. What if I have 257,000? I'm still a 500 kilogram. I'm still on the Earth, 9.8. What's the height of the first hill? Let's just do that division there. 257,000 divide 500 divide 9.8 gives me here 52.5 meters, or 53 meters if you round that there. So that's going to be the height. You'll notice that it is taller than 30 meters. Basically, I transfer some of that moving energy back into getting me off the ground. So that's why it's a little bit higher than the beginning. And then for part C, if I did this really accurately in this question, part C was after I had lost a little bit of energy. So for part C, I'm going to use the 24/7 number here. So part C, my fastest speed is when I'm going to be back on ground level. Remember, for these problems here, we can set ground level to something that's convenient, h equals 0. In this case, at ground level, I have no more money in the potential account. What if the whole 247,000 is actually all kinetic? I know the formula is half mv squared, so we're going to go 247,000. Had it not been for air resistance, I would have done 257,000. But let's figure out the maximum speed here. I'm 500, and this one here is, I want to find the final velocity. So 247,000 times it by 2, divided by 500. So 988 is supposed to be v squared, and that gives me my final velocity as 31 meters per second. And as expected, this speed here is faster than the speed I had at the first hill because some of that energy was still locked away in that hill there. Right? Okay, so that practices for us are two formulas for work. One is force times distance. The other is change in energy. We dealt with this work energy theorem. Were it not for any work, energy is also conserved. It being a scalar, I just basically need to add up all the numbers. Right? So two last styles of problems here. One I want to do with you is a pendulum question. So in this pendulum style question, we're going to have a pendulum hanging off a roof. Let's say this time our pendulum, the string itself is a 3-meter long string. Okay. The bulb on this pendulum here is 4 kilograms. I'm going to say that this pendulum is at rest. I'm going to start off with a bullet again. This bullet here is going to be 200 grams. It's zipping by at 60 meters per second. Right. I'm going to tell you that's the before picture. The after is the collision is actually inelastic. Okay, so that's the before. Afterwards, so before, the after picture is I have my string. The bullet gets sort of intertwined with the bullet itself, perfectly inelastic. I'm now going to be 4 kilograms plus 200 grams. So I'm now going to be a 4.2 kilogram mass. And now this pendulum here, it's going to have some velocity upon leaving here. And it's going to start swinging upwards, assuming the swing doesn't snap the string here. We want to actually calculate what this theta here is. Right? So let's just go through here. Part A, calculate the speed at the bottom. So when the bullet inelastically intersects with the block, what's the speed going to be? B, find the angle the bob makes with the vertical. So from the straight up and down, how far in front of the vertical does it get? We can assume this is the maximum distance, so this one here is going to be at rest. All right. So again, I encourage you to pause the video, try it out for yourself. First part here is actually dealing with the collision, so we actually need to do momentum conservation. So P in is supposed to equal to P out. At the beginning, I had two objects, M1, V1, and I had a bob, which is M2, V2. Later on, it was M1 and M2 altogether times this velocity. Notice that this velocity is just immediately right after the collision. I haven't even dealt with the swing part of the motion yet. If anything is not in the correct SI units, let's convert it first. So 0.200 kilograms, 60 meter per second here is already SI unit, so that one's fine. So I have a bullet that's 0.200 kilograms. It's coming in at 60. My mass is 4 kilograms, but it's at rest, so 0. Later on, that's where I got my 4.2 from. I took the 4 and I added this 0.200. Let's find out what the final velocity is supposed to be. So 0.2 times 60. Overall, I have a tendency to stay in motion of 12. The blob at rest is just going to be 0. This is going to be 4.2 V total, and therefore the V total as it leaves, 12 divided by 4.2, gives me here 3.3 meters per second. So just based on a conservation momentum, it's considered whether it's an inelastic problem or even an elastic problem here. Now what's going to happen here is a conservation of energy style question. Afterwards, we're going to actually be traveling the maximum speed here. So let's find the EK at the bottom. EK is given by 1/2 mv squared. 1/2, my total mass is actually 4.2. My final speed that I calculated from momentum conservation was 3.3 squared. 0.5 times 4.2 times 3.3 squared. This one here gives me 22.9 joules. I have 22.9 joules of moving energy. All that's going to happen here is as I swing upwards, I'm going to define H equals 0 to be here. So that's why I could say there's no potential at the beginning. The ground really could be down here, but it's relative anyways. So if H equals 0 here, as I swing upwards, as I start picking up some vertical height, I start transferring some of my energy from my kinetic account over to the potential account. And as it hits the potential account, EP at the top is equal to mgh. If all the 22.9 was transferred to the potential account, 22.9, I'm a total mass of 4.2, assuming we're on the Earth's surface again, 9.8 times h. The h, the maximum vertical height that I get, take the whole number if you have it, 22.869, divide 4.2, divide 9.8, gives you a total height of 0.56 meters. Right? Again, be really careful here from this formula here. Potential energy is going to be mgh. Mgh here, this is the vertical height. It's sort of how far from ground, even though I'm sort of making this sort of curved angle here. And now we're ready to just sort of finish off the problem here. If I know that this string in total was 3 meters, by the time I make it up to the top, the vertical height that I reach is a height of 0.56 meters. I can create a new triangle here. Then this vertical bit here would be 3 minus 0.56. So 3 minus this answer here, roughly 2.4 meters. If I know this side of the triangle is 2.4, remember the bob is still on the string here. It's just going to swing upwards this way. 3 meters going up and down, you swing upwards. This hypotenuse side is still 3 meters. We can then use our inverse cosine to find that angle there. Cosine of theta is supposed to be adjacent over hypotenuse. So therefore theta is the inverse cosine of the adjacent, the side that's right beside me, 2.4, divided by the 3. And therefore we get theta, inverse cosine of 2.4 divided by 3 gives me 37 degrees. While you're tempted to say, oh, we're from the pure south direction, we're east of south, remember this is a side view problem. So we're talking about like vertical and horizontal here. So this is 37 degrees, just sort of forwards from the vertical. 37 degrees maybe in front of vertical. Right? Or just draw a picture and you can label where that theta is. Okay? I'm going to leave you with one other style of question here. We switched over to thermal energy for a little bit Basically, heat is passing energy from one object to the other object here. We dealt with another conservation style problem with the thermal energy problem. Let's just do it by example here. Let's imagine I have a metal. This metal here is 80 grams. The specific heat I'm going to give you is 0.60 joule per gram Kelvin. That's a constant for the material. Some materials are just easier to heat up. Some materials are a little bit harder to heat up. Currently, I have this block here at 50 degrees Celsius. I'm going to drop this into a beaker of water. For the water itself, let's say I have 200 grams worth of water. The specific heat here is 4.18 joule per gram Kelvin. That is a relatively high number. Water has a really high constant. It's really hard to heat up. It's really hard to cool down. So that's why the 4.18. And currently the water is at 10 degrees. What I'm going to ask you to calculate is, as you drop this object in, heat is always going to go from hot to cold. So hot to cold. Our formula is essentially Q is equal to mc delta T. Using a sort of conservation style, basically I have this hot metal block. As you drop it into a cold cup of water, the heat is going to emanate and it's going to leave into the water. I'm just going to start you off here, and then I'm going to let you try it out for yourself here. We're going to be under the impression here, whatever heat that this metal block loses is actually going to match up the heat that the water actually picks up, water gains. So because both of these are Q's, it would be mc delta T has to be mc delta T. You're going to actually punch through your values. Normally, we would be worried about grams because this one here is not the correct SI units. But you notice the specific heat is actually also per every gram. If I have 1 gram cube and I want to heat up that by 1 step on the Kelvin scale here, this is the amount of energy that I need, the grams would actually end up canceling out. So totally okay for you to put 80 grams. This is going to multiply the specific heat, 0.6 joule per gram Kelvin. The delta T's are going to be different. The delta T's are always going to be final minus initial. Initially, this one here was 50. So this means 50 to whatever final temperature. Whereas for the water, it started out at 10 degrees. This is actually going to go 10 degrees to the final temperature. Heat is going to continuously pass until they have the same final temperature. We call that the equilibrium temperature. So as you finish this off here, I want you to calculate the equilibrium temperature. What temperature do they both settle out at? I'm expecting it to be something between 10 and 50. So calculate the unknown as TF. As you're writing this formula here, you're going to go TF minus 50. On the other side, the mass of water was also 200 grams, 4.18 joule per gram Kelvin. And this one, TF minus 10. The TFs will be the same. The equilibrium temperature, heat is going to pass until they're the same temperature. Remember, however, I just want to hint at this here. The direction is actually different. One of them, heat is actually lost. Let's say the metal here loses 5. It's negative 5. The water picks up that, right, to make sure energy is conserved. That has to be a positive 5. I can't say negative 5 equals positive 5. Remember, one of these sides has to be negative. So don't forget to add the negative before you try to solve your way through for TF. Okay? So I'm going to leave you at that point there. You can try to work your way through the thermal energy problem. Keep practicing through your worksheets, and we'll go from there. Thanks, guys. Take care.